morning, I am Renu Sharma, Assistant Professor, EC Department. Today I am going to start with the next part of Unit 4, that is related to line coding, and before that we will discuss delta modulation also. So, delta modulation is the sampling rate of a signal should be higher than the Nyquist rate. So, that is the main criteria when we consider a sampling condition where sampling frequency should always be greater than equals to 2 FM. Now, that is known as Nyquist criteria. So, if this sampling interval in DPCM, that is differential pulse code modulation, is reduced considerably, the sample to sample amplitude difference is very small. So, as if the difference is 1 bit quantization, then the step size is very small, that is denoted by delta. So, this is nothing, this is the step size that we have to consider in case of delta modulation. So, whenever we are going to sample the signal, samples are taken at constant interval of time, and then these samples are being are divided into different step size. Now, step size can be variable, it can be constant also. So, delta modulation, it is the type of modulation where the sampling rate is much higher than the and in which the step size after the quantization is of smaller value. Such a modulation is termed as delta modulation case. So, features of delta modulation are: an oversampled input is taken to make full use of the digital correlation. Another feature of delta modulation is quantization design is very simple, it is also known as 1 bit quantizer. The quality is moderate and the input sequence is much higher the rate than the Nyquist rate. So, that is the all the criterias are fulfilled, then we can consider that it is a kind of delta modulation case. Also, the design of the modulator and demodulator is very simple. The staircase approximation of the output waveform is there, the step size is very small. So, these are some of the points that is related to the delta modulation. So, then we will see what is delta modulator. So, it comprises of a 1 bit quantizer and a delay circuit along with the 2 summer circuits. So, this is the block diagram of the delta modulator. Now, you can see that at the input of this DM delta modulator block diagram, there will be an oversampled input signal that is denoted by X and TS. So, XT will be the input signal, and when we are going to take the samples at equal time interval, then it will be known as X and TS. Then the output of this will be an error signal, which is nothing, which is the difference between the input signal and the signal which is generated, which is the predicted one. So, that is the predicted signal. Now, the subtraction of these two will make up will produce an error signal whose value is given by EP and TS. Then it will be applied to a 1 bit quantizer block. Now, the output of this will be equivalent to EQ and TS, that is equivalence to V and TS. So, that will make up a output of DM. Then it is applied to an delay circuit. Now, delay circuit is basically applied because it will going to compare, it will going to predict the output value depending on the comparison with the previous sample that has been taken. If the step size is increased, now let us say this is the waveform, this is a staircase approximation that we have developed after the sampling operation. Now, in this case, the delta modulator will going to compare the next sample from the previous sample. So, that is why we have used a delay element in the feedback path. Then this will be compared when it will be increased from the previous sample, then +1 will be transmitted, and let us say this is the case, then 0 will be transmitted. So, this is how the prediction will be done. So, for each sample we are transmitting only 1 bit of information. So, that is known as 1 bit quantizer, that is delta modulator. So, the predictor circuit in DPCM is replaced by a simple delay circuit in DM. So, that is the difference between differential PCM and DM block diagram. Then from the given diagram we have these notations, like first one is the XNTS, that is the oversampled input, that is the sampled version of the input signal, that is XT. The next one is the summer output and quantizer input, that is the error signal, and the main aim of designing this circuit is to minimize this error as low as possible. Ideally it should be 0, but practically there is some value depending on the value of input and the feedback circuit. Now, next one is the quantizer output. So, the output of the quantizer is denoted by VNTS. This is nothing, this is the bits which are been predicted by comparing the step size of the signal and the previous signal. Then output of the delay circuit will be there, that is the predicted value. So, this is denoted by X cap and TS. So, that is basically the approximation of the actual bits. This is not the actual bit, this is just the approximation of the signal. Next one is UNTS, that is input of the delay circuit. So, using these notations, now we can figure out the process of modulation. So, these are some of the equations that is related to the diagram that we have seen in the earlier slide. So, first equation is related to the error. EPNTS is equals to XNTS, that is input signal, minus the predicted value, that is X cap and TS. So, this is equation number 1. Second one is XNTS minus UN minus 1 TS. So, you can see this this XNTS can also be is related to UNTS, because when UNTS is applied to a delay circuit, then there is a delay of one element. So, that will be UN minus 1 TS. So, that is how this X cap and TS can be replaced by UN minus 1 TS. Now, next is this again UN minus 1 TS can be replaced by this value, that is X cap and minus 1 TS plus this one. Further, this will be equivalent to EQ and TS, that is since it is passed through a 1 bit quantizer, then the output bit, that is V and TS, is equivalent to the error signal. So, after solving this, this equation will reduces to U and TS, that is the output of the feedback circuit, the output of the delay element, and it will be equivalent to UN minus 1 TS plus VN TS. So, which means that the present input of the delay unit is equivalent to the previous output of the delay unit and the present quantizer output. So, that is the main formula by which you can decide that whether 1 is to be transmitted or 0 is to be transmitted. So, we are assuming a 0 condition of accumulation. What is accumulation? Accumulation is the accumulator is basically a circuit which you have seen. This one is the accumulator circuit only, which consists of a delay element in the feedback path. So, the formula, the output of this accumulator will be UNTS, that will given by this equation, that is summation J's from 1 to n signum function of EPJTS. Now, the accumulated version of the DM output will be given by this equation, that is VJTS from J is from 1 to, and so that is the case for accumulated version of DM output. Now, the delay unit output is an accumulator output lagging by one sample, why lagging by one sample, because we have used a delay by 1 unit only. So, when the input is UNTS, the output will be UN minus 1 TS. A staircase approximated waveform will be the output of the delta modulator with the step size as given as delta. So, the output quality of the waveform is moderate. Now, next we will see this is the receiver part of the delta modulator, where again accumulator circuit is used in the feedback path, where we have used this delay by TS, means by 1 unit delay. So, the delta demodulator comprises of a low pass filter, a summer and a delay circuit. So, basically it consists of low pass filter, a summer circuit and a delay by TS. So, the predictor circuit is eliminated here, and hence no assumed input is given to the demodulator. So, that is the following diagram for the delta demodulator case is there. So, that is the input of this summer, that is V cap in TS, is followed by the output of this will be a U cap and TS, that will be the summation of U cap and TS and X dash and TS. So, that will be the output of low pass filter. Now from the above diagram we have the notations, that is VCAP and TS is the input sample, this is the summer output, and this will be the delayed output. So a binary sequence will be given as an input to the demodulator. The staircase approximated output is given to the low pass filter. Basically the low pass filter is used for many reasons, but the prominent reason is noise elimination for out of band signal. So let's say when we have approximated the signal, this is a kind of staircase approximation, and we want to find out the input waveform. So when this particular approximated signal, that is a kind of xt only, is out of the range, then at the transmitter side, then it constitutes a noise that is known as granular noise, and it is a kind of ideal noise only. So which is eliminated here. So if there is no noise present, then the modulator output equals the demodulator input. Next is advantages of DM over DPCM. So delta modulator advantages, first one is 1 bit quantizer. Then next is very easy design of modulator and demodulator circuit, because it requires only 1 bit quantizer. So however, there exists some noise in the DM. So these are the two drawbacks, you can say, or the two noises that are present in the delta modulation because of the fixed step size which is considered in DM. But as far as this step size is concerned, when it is variable proportional to the rate of change of the message signal, then it is known as adaptive delta modulation, and in that case these two noises are not present. So the noise which is present in DMR, first one is slope overload distortion when delta is very small, and granular noise when the delta is very large. So this is the case when delta is not changing directly proportional to the rate of change of the input signal. Next one is adaptive delta modulation. In this case the delta is variable. So we have come across certain problems of determining the step size which influences the quality of the output wave. So this is the main diagram of this ADM, generation of ADM. It constitutes this summer, then it is followed by an amplitude limiter, then a sampler is there. To sampler we require a clock signal which will take the samples at equal time interval, that is denoted by Fs. In the feedback there will be a voltage controlled amplifier, then this will be followed by an integrator, and the output of this integrator will be present at the input of this particular summer. So this will be an adaptive delta modulated signal, output will be there. Now the gain of the voltage control amplifier is adjusted by the output signal from the sampler. The amplifier gain determines the step size, and both are proportional. So ADM quantizes the difference between the value of the current sample and the predicted value of the next sample. So basically in case of ADM there is no option, or there is no drawback is there of the two noises which are present in DM because of the variable step size. Now next we will see another topic. After this there is line coding. So line coding is just a kind of technique where you can convert the 10 bit, that is digital information, in the form of electrical signal, so that it can be transmitted over the channel. Now channel can be wired or it can be wireless. So as the coding is done to make more bits transmit on a single signal, the bandwidth used is much reduced. So for a given bandwidth the power is efficiently used, the probability of error is much reduced, power density is much favorable, and the timing content is adequate. So these are some of the properties that are associated with the line coding. Why we are going to learn this line coding. So types of line coding, majorly, or you can say in broad sense, this line coding is divided into three different techniques. Like first one is unipolar, polar and bipolar. So unipolar is first we will see unipolar. In case of unipolar signaling, it is also known as on off keying or OOK. The presence of pulse represents bit 1 and the absence of pulse represents 0. So, that is very simple kind of line coding. So, first we will see what is unipolar, polar and bipolar. In case of unipolar, we have to consider only one amplitude level, either plus A or minus A. So, let us say this will be 0 axis, this will be plus A, this will be minus A. So, to transmit bit 1, we have to consider this plus A, and to transmit bit 0, the output will be 0, or either we can consider minus A and 0 for 0, this is for 1, this is for 0. So, either way we can consider either plus A or minus A. So, that is the following figure that will depicts the unipolar case. So, this is a clock signal, these are the data, like this is 1 0 1 0 0, and you have to convert it into unipolar NRZ. Now, NRZ means this is non-return to 0. So, non-return to 0 means for every bit transmission you require a time, that time is denoted by bit duration TB. So, for after the half bit duration, if the signal again comes to 0 origin, then that is known as return to 0, and when it does not comes to origin after half bit duration, then that will be known as NRZ. So, that is the case of unipolar NRZ, like for 1 bit you are transmitting voltage V, and for 0 you are transmitting 0 volt. So, that is the unipolar NRZ. Advantages is it is simple, lesser bandwidth is required because you require voltage for the transmission of bit 1 only, you are not transmitting anything for bit 0. Disadvantage is no error correction is been done, no clock is been present, and there is loss of synchronization if longer bits of zeros you have transmitted, because for 0 you are transmitting 0 volt. Now, next one is unipolar RZ. So, in this case you can see that for after half bit duration the amplitude will return to 0 for bit 1. Again this will return to 0 after half bit duration. So, that is unipolar RZ. Next is advantages of unipolar RZ. It is again simple, the spectral line present at the symbol rate can be used as a clock. Disadvantages is it requires no correction, occupies twice the bandwidth as the unipolar NRZ. So, this is the polar NRZ case where you require both the voltage levels, plus V and minus V. So, for bit 1 you are transmitting from minus V to plus V, and for transmitting 0 you require plus V to minus V. So, this is how alternatively you require voltage levels. Now, these are the advantages of polar NRZ, that is it is simple and no low frequency component are present in this. Higher frequency components are present, and also the disadvantage is no error correction is required and no clock is present in this case. Next one is polar RZ. This is the same case, like you can see that this is plus V 0 and this is minus V 0 for the half bit duration. So, these are the advantages of polar RZ. Next is bipolar case. Now, in case of this bipolar, you require all the positive voltage and negative voltage both, but this is also known as alternate mark inversion. Alternate mark inversion means for first 1 bit you are transmitting plus voltage, for next 1 bit you are transmitting minus voltage. Now, for again 1 you are transmitting plus V, and for next one you are transmitting minus V. So, that is alternatively you are changing the sign for transmission of bit 1. In the same manner you can make the RZ waveform. These are the advantages. It is simple, no low frequency component is present, a single error detection capability is present in this case. So, this is all about today's lecture. Thank you.